away we go with question 3 then. Okay, so steam is cooled from an initial temperature of 150 degrees C. Calculate the initial temperature of the steam in Kelvin. Alright, now this formula is not in the data booklet. You are going to have to learn this formula. Okay, and it is T, which is the temperature in Kelvin, equals theta, which is the temperature in degrees C, plus 273, which is the conversion factor between the two scales. Okay, so there's no shortcuts here. You are going to have to learn that formula, and then it's very straightforward. You just substitute 150 plus 273 gets me a total of 423 Kelvin for 1 mark. Next bit. Okay. So it says that the steam is changing and it eventually becomes ice. Okay. So what processes is it going to go through then? Well, up here, okay, this is where it's steam and cooling down. When it's C, it's water and it's cooling down, and then E is where it's ice. So the phase changes are shown by these boundaries here. So D is the freezing point of water, and B is the boiling point or the condensation point of steam. Okay, so the changes of state occur at B and at D. Did I miss a question? No, keep going. Describe the differences in the arrangement of particles when the sample is in steam and in ice. You may draw a diagram to help your answer. So I'm definitely going to do that, because a picture's worth 1,000 words. Okay, so you can see that the way that I'm drawing this is all of the particles are the same size and they're all in a regular pattern. Okay, so they're all lined up in a regular pattern with each other. Okay, and it's important that I label up this diagram. If you don't label the diagrams, the examiner doesn't know which way around they are, and you don't get any marks for it. And then for steam, okay, then well, there you go. That's probably enough particles for the gaseous phase. Okay, you can describe it in words, but there's two, very distinct things that you're going to have to try and communicate. So the particles are much closer together in a solid, basically touching, and much further apart in a gas. So the intermolecular spacing is much larger in a gas. And then the other thing that you need to get across separate, because it's 2 points and we've got to talk about the arrangement. The other one is this idea that it's a regular pattern in a solid, okay, but it's irregular and random distribution in a gas. Much easier to get 2 marks by drawing yourself a quick diagram there. Okay, explain whether or not the energy in the kinetic store of the particles changes when the sample is changing state. Now this is an interesting one. I'm going to go back to the graph, okay, and let's have a look at what happens to the temperature as we go from that point on the graph to that point on the graph. Okay, so this is the way that we're kind of going down the graph. This is time increasing, yeah? So that's the trace on the graph, and you can see that it's going to go from this point to this point. What happens to the temperature? Doesn't change at all, does it? Now you might remember a 3-mark question about this from paper 1, and it was that the Kelvin temperature is directly proportional to the average kinetic energy of the particles. So that means because the temperature does not change, in a change of state, then that must mean that the kinetic energy does not change during a change of state, which is quite difficult to get your head around really when you think about it, isn't it? Because if the temperature stays constant, that means that the particles are moving just the same speed, which means that the kinetic energy is the same. So what is it then that must change? Well, of course, there's more types of energy than just kinetic energy. And what happens is that as we're going from water, okay, where the particles have got very close spacing, but they can basically kind of slip and slide over each other. Okay, then we're going from that into a regular fixed lattice structure, okay, of ice. Okay, so there's much stronger intermolecular bonding between there. So what we're doing is when we're cooling in these phases, you know, like if in section C, then because the temperature is changing, we're changing the kinetic energy, the average kinetic energy of the particles. We're reducing the average kinetic energy of the particles because it's in a cooling phase. Whereas here, we're reducing the potential energy that those particles have. Those particles and there's bonds being formed between the particles. And the same when we get to ice, as it cools further, the temperature starts to change again. So now it's not the potential energy that's changing anymore. They're already fixed in that lattice, okay, but the vibration in the lattice decreases as we go through section E of the graph. Okay, and that's all you need for 7 marks.